All right. We were talking yesterday about free fall, where gravity is the only force acting on an object. Now, remind me real quick. Gravity on our planet makes objects accelerate. That's indication that there's a force acting because it makes stuff move or change motion somehow. How fast does gravity make us accelerate? 9.8 meters per second squared. Okay, we're going to keep driving that in. Now, if you were to take an object's mass and then you multiplied it by gravity, that 9.8, you get kilograms in mass times meters per second squared, which is ugly unit of kilogram meters per second squared.
Is that newtons, right?
That's a newton.
Yeah.
A single newton. Now, the units are ugly conceptually, though I do want to remind you that they're kind of nice when you think about it. A single newton of force is what it takes to accelerate a 1 kilogram object at 1 meter per second squared. That's it. So imagine a 1 kilo object, how hard you have to push to get it to accelerate at 1 meter per second. It's not much. That's a single newton. Okay. Now, yesterday we watched a couple videos. The whole point of all the safety equipment in a vehicle is to make that crash do what?
Slow.
So slow down or take longer. It lengthen the time so that your acceleration gets smaller and therefore the force that you feel also gets smaller. Okay. Beyond that, we watched somebody jump from space, right?
Yeah.
Okay. And then we talked briefly about free fall. Now, when we look at free fall, gravity is the only force acting on a falling object, which means, do real skydivers experience free fall?
No.
Not really, because what pushes against a skydiver as a skydive? Air. Air resistance doesn't truly work if we're talking about free fall. Now, free fall, this is going to be super weird, because when everybody thinks about free fall, I imagine the ultimate conclusion of free falling is like splat, right? Probably. Here's one nice little piece, though, that's just interesting to think about, but we've spoke about it briefly. Orbit around our planet is free fall. Now, that can be like oddly misleading because obviously we have stuff orbiting the planet that's not just crashing into us all the time, I think. I don't see anything crashing into us. I'm pretty sure of that. Okay, what that means for us is that when we orbit, all we're really doing is orbit is free fall, specifically falling perpendicular, which means what? So this is a symbol. You guys have probably seen this symbol before. Maybe not. Okay, that's a symbol for perpendicular, not like a me thing. That's a real symbol. 90 degrees. Like you said, it's this, right? If you think about this is probably what you guys think of perpendicular. It's at 90 degrees. Falling perpendicular to gravity. Or specifically the force of gravity. But all that orbit is just falling in a really specific way so that you never land. That's it. Okay. Beyond this, some things worth mentioning in free fall. And the vomit comet was a good example of this. That's pretty close to being able to experience free fall because inside of the plane that you're flying in, do you feel the air? No, the plane feels the air, but you don't feel it, so there's no air pushing against you specifically. Those people look weightless, and they feel weightless as they go, right?
How do you breathe there?
So there's air in there, but the air inside the plane is moving at the same speed as the plane. Same reason that it's not crazy windy while you're flying, like to Anchorage, right? But the same thing happens there. As you look at it, weightlessness is a terrible name for stuff. Because remember, weight is the force of gravity that you feel. Do you really, not the force of gravity that you feel, the force of gravity that acts on you. While those people are in the plane, that vomit comet flying, is gravity still acting on them? Do they still have a weight then? Yes, but they're under this idea that they feel weightless. They're not. Obviously, they still have to weigh something. Make sure that we're cool that weightlessness is a sensation, not real truth. Okay? Same thing happens in an elevator. When you're on an elevator and it starts going down, what do you feel? No, maybe you feel lighter, I imagine. Because as it starts moving downward, you feel your organs probably want to stay where they're at and your whole body goes. That's that feeling in your gut when you're going up or down really fast. But their skeleton stays or something? Yeah, exactly that. Yep. I mean, not exactly that. Skeletons don't really spit out of our body. But okay. So, free fall. Seemed okay? All right. Now, beyond free fall, we have talked so far about Newton's laws, talked a lot about them. The most important, and this isn't really a truth, but what I consider the most important of these laws is rule or law number 2. F equals ma. That's like the big one that we deal with. What's the first one again? Inertia, which means
I think that in motion stays in motion.
okay, in motion stays in motion. Then force is mass times acceleration. What's that third one?
Something opposite but equal force.
Good. Every force is, if it's not moving, is equal and opposite. So right now, this is pushing down on the table, but the table's pushing back on it. Hence, it's not flowing through. Okay. Now, these next few sections are going to be super short, but they don't really link perfectly together. I'm going to change color, though. You guys ever been to a carnival?
No.
You've really never been to a carnival?
Never been to one.
Okay.
I've never been on a roller coaster or fair, so never been on
Okay.
Yeah.
Interesting. They're okay. You guys have seen those rides that spin really fast and like it pulls you against and it's really hard to sit up?
You can like climb up kind of.
Yeah, depending, right? Depends on how fast it goes. Is there any physical object pushing on you? But are you getting pushed?
Yes.
What's causing it? So why? So you're right. We'll call it the G-force. Love it. What could cause it though, right? Because something should probably cause that force. Wouldn't you agree? Okay. So do you guys know what that actual force is called? All right. So there's two different ones that we deal with in here. If I say a centrifuge, do you guys know what that is?
Centrifuge.
A centrifuge. So when I think of a centrifuge, I think of a big fancy like medical device where they put blood in and it spins really, 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 really fast. Like maybe you've seen them, maybe you haven't. It's how you can separate blood and blood plasma out of blood, but you guys are looking at me like maybe not, so that's okay. As we're going with this, there are two different types of forces that we see dealing with specific turning motion. We have centrifugal or centrifugal, like a centrifuge, and then we also get to talk about today this idea of centripetal. Centripetal force. Now, as we look at things, really everything, have you guys ever turned a corner? Yes. So obviously, right? That's a silly way to word it. But if I'm in a car, and I think we talked about this earlier, didn't we talk about centripetal acceleration?
I think so. Oh, you turn a corner like.
Definitely did, because we talked about the sloshing of the liquids as you're turning. I bet if you look back, you'll see a centripetal acceleration defined. Now, as I'm turning, I'm going to turn this way. I'm changing my position, which means I'm definitely, like I'm accelerating. I'm changing the direction I'm going. And then what's really commonly linked with acceleration, according to Newton at least?
Velocity.
So definitely. But there's another big idea of Newton, something to do with acceleration. Maybe mass also.
KGMS.
Force is mass and acceleration, right? So as I'm turning this corner, what we wind up seeing is we're dealing with this idea of centripetal force. So lots of things travel in circular paths. So for example, our space station orbits our planet in a circular path. What keeps it going circular? Gravity. Gravity pulls it in, right? But we're falling in that certain way. When we talk about centripetal force, it is always going to be connected to some sort of rotation or turn that we're undergoing. Specifically, we're going to say that centripetal forces, in our purposes, are forces that are exerted toward the center of a curved path. Okay, toward the center. Easy to remember, centripetal, center of a curve or a circle. Now, how this shows up and the cause of this, it varies a lot. So cars are an example of everyday things that we always see turning and going around circular motion, whether it's a perfect circle or not. So it's worth mentioning, and I'm just going to say as a follow-up, many possible causes for this. Okay. Exerted, toward the center of a curved path. So I'm going to just round the corner here real quick, and I'm going to have to use centripetal force to do this. But what causes it may not be immediately obvious. Here I am, I'm turning. Right now I'm accelerating that direction to make me turn. If I push that way, right now my acceleration is going towards the center of that circle because I have to push myself that way. how do I generate the force that allows me to turn? That's my centripetal force. Like, can I just make it here? I can't centripetal force myself right now. I'm moving my feet. They're not centripeting right now. I don't. What do you mean? It definitely goes through my feet. You're right. How do my feet and your feet, anybody's feet, actually generate the motion that we're doing?
Push down.
I rely. It's not so much as pushing down necessarily. I do have to push down. What is this called? If I do it more obnoxiously, you'll notice it. Dragging. Use a different word. It's friction. We're able to turn because we use our legs and our muscles to create centripetal force through friction. Like, that's the only way that we do it. If it's super duper icy, can I make that turn?
Maybe not.
If it's like super wet ice, I'm not going to make that turn, right? Like, I'm just going to fall or just keep going straight no matter how hard I try. So, friction is a really common cause of this centripetal force. Friction. Specifically, it's all over the place with regard to this. Cars turn often, just like people, right? Friction is generated by my feet. What generates the friction in a car? The wheels or the tires, right? Which, like, when you think about bad tires that's not on a racetrack, if you have no tire tread, you're in trouble, right? Because less friction. Yes, sir.
Are burnouts friction?
Are they friction? Definitely. Yes. Cool. All right. Now, friction, whether it's a tire or a shoe, doesn't matter. It's a force pushing this direction to make us turn. Can you think of any other things that turn? Like, what is causing the centripetal force for orbit? Like, the space station doesn't just shoot off. Why do they keep turning toward the planet? Gravity can produce this centripetal force. Anything else? What generates the centripetal force as we're going on that spinny ride?
The motor. I don't know.
So the motor generates you moving, and the velocity certainly generates some other stuff as well, but it's the walls themselves that are generating that force. Now, the walls push in, right? Like, when we turn, it doesn't feel like it. The walls don't physically close in on you, but if I'm turning like this, there's a force pushing this way. And if the wall is pushing on you that way, it feels like, identically, because student third law, it feels like you're being sucked into the wall. It's just the wall physically pushing on you is what you're feeling. Okay, as we go through here, dealing with circular motion, centripetal force. Okay, feel okay, feel awful? I'm just trying to blast through so we have time to make sure we can work on stuff. Okay, beyond this, in this section, I hate the way they do it, but it just kind of splits up into like 4 different things really quickly. We have discussed free fall, no air. Centripetal force towards the center. Cool. Moving forward still, we have been talking a lot about force, and we're going to keep talking about force. There's another idea, though, that deals with it. If I drop this on Riley's fingers, is it going to hurt? Did it hurt? Okay. I'm not really going to drop it. I wouldn't. Why? Why would I do that?
Because you know bigger mass.
Ooh, why would I care about a bigger mass? So it's heavier, and why would that?
Higher acceleration.
So no higher acceleration, definitely not. No more gravity either. Regardless, they both accelerate due to gravity at 9.8 meters per second squared. But there's something different about it.
Less air resistance.
So maybe more mass means more force, right? Because mass and acceleration. Now, beyond that, there's another idea that we've seen having to deal with how heavy something is and how fast it's moving. No, not just velocity. Momentum. Okay, when you look at momentum, it's mass times velocity. So it's a very similar idea, kilogram meters per second instead of kilogram meters per second squared, right? Like, that's the only difference between momentum and the other idea, force. Specifically, though, they both have a lot in common. It's just how heavy is something and how quickly does it move. One's velocity, one's acceleration. When we look at this, we're going to do some fancy stuff that happens all the time in here, which is going to feel like a math class for a minute. 2 things that needs to remember. Newton hooked it up. How does one find force? Mass times acceleration. Sorry? It doesn't matter whether it's the force of gravity or not. If it was a force of gravity, it'd be Fg equals mag. Absolutely. Okay. And remind me real quick, what is rho or momentum?
Oh, velocity over mass? Or
Not over.
Times velocity.
Okay. These both have to deal with how heavy something is and how it moves. What's the difference between velocity and acceleration, though?
One has a direction.
No,
So they both do.
Oh, wait.
One's per second squared. One. What?
One is how
One
fast,
moves at-
the change in how fast it's going, and
Yeah.
one is how fast.
One's how fast it's going.
So
one's,
I love where you started. We're going to clean that up.
no.
Check it out. Velocity is a change in your position. And acceleration is a change in your what?
Speed.
I use a better word. Not speed. There's a better word than speed.
Acceleration.
Acceleration is a change in not speed. You're not wrong, but there's a better answer.
It's like-
Velocity. Okay, so they're obviously related. As we look at this, we're going to even do a little bit more. Can somebody remind me, and this we just briefly talked about it, but not exactly. I want us to recall three things here. I have A, acceleration. How do you find acceleration?
F over M. Force over mass.
So careful, don't guess. And that's a great answer. You are absolutely right. That's not the one I want to use, though.
Oh.
You're right that it's A is equal to F over M. But as a definition, we said it's a change in something over a change in something. We just said it a second ago. Can you remind me?
A change in velocity.
Okay, which we could write as delta V. But do you guys recall doing VF minus VI to find delta V?
Yeah.
And it's just over some amount of what?
Time.
Time. Okay. So we're going to keep these in mind here real quick. And one of the really common things that happens in physics, which this is where it's going to feel really mathy, it almost feels as if you're cheating sometimes. Because we're just going to use known stuff and substitute in all over the place to try to make sense of different situations and see how they shake out for us. Now, very specifically, are force and momentum similar ideas? Like if I asked, would you rather be hit, like I could drop a bowling ball from here or from 10 feet higher onto you, where do you want it to drop from? Lower, right? Because one, there's less force when it hits you, but you could also argue there's less momentum when it hits you. Okay, so as we look at this, you're absolutely right, and that's due to that momentum and the velocity and all those different things. We're going to do some rearranging. This is really common in physics. So some rearranging. Now, it took a lot of brilliant people over a long time to work out these different convenient ways to do this. It's going to feel like I'm just picking at random. I promise I'm not picking anything at random, but you guys aren't physicists discovering this stuff for the very first time. I don't expect you to be able to do it at random like they do. Okay, I'm going to start with force equals mass times acceleration. And I know that this statement's true, but is it possible that maybe there's a point in time where I just don't get the acceleration? Like, I know the mass, but I don't have the acceleration given to me. Like, I can think of it, a 5 kilogram object traveling, but I'm not going to tell you how fast it's accelerating or not. Okay, if I wanted to, is there anything up here that I could replace this A with? We could use this, couldn't we?
Yeah.
Like, this is still acceleration, right? And this is acceleration. Could I replace this A with this expression? Yeah. Let's do that. And again, I know it feels super random, but I promise we're going to make a connection here. This would become mass times, and I'm just going to replace it here. VF minus VI all over T. Okay, with the conceptual idea, you may not understand its significance. Mathematically, are you guys okay? Okay, so here we may really test your math ability. When I see M and then in parentheses I write that other thing, what's happening between them? Okay, here's the harder question. How do I do that?
Distribute.
Ooh, I distribute. What is the M going to wind up connecting to?
All three. I think everything, right?
Okay, I'm
We're
going
going to do
to suggest
first.
3 options to you guys. I want you at your desk to argue in favor of one of them, okay? When the M distributes, it's going to. It has 3 options. It goes to everything, just the numerator or the top, or just the denominator at the bottom. Which of those should it work with when we do multiplication? I'm going to give you a second. Chat it out. Is this M right now, is it a fraction?
No.
We didn't write it as a fraction. Could we write it as a fraction? Okay, I'm going to do scratch work over here. Don't write it down over here. But I think M over 1, right? Times, and I'm just going to use times instead of parentheses. I lied. I have to use parentheses still. VF minus VI over T. Hate it. Love it. Okay. Here's my question again, though. It's going to feel a little bit different. How do you multiply these? How do you multiply fractions?
Cross. Keep changing.
So I hate the language that you're using. I wouldn't say cross. Straight through?
Straight through, sure.
Top to top, bottom to bottom?
Yeah.
Because cross, I'm trying to avoid because you're going to confuse somebody with what? Cross multiplying like you do with
That's
proportions.
what we call the key change.
Okay.
Yeah.
So I'm just going to go straight through. Do you agree that this multiplies to the top and this multiplies to the bottom?
Yes.
Okay. Which means when we come back here, if I wanted to distribute, and I'm going to real quick, and I'll stick with orange here, this M winds up distributing to here and here. Do you guys agree?
Yes.
All right. So let's just see where that takes us. We're left then with force is equal to, and this is going to be an ugly fraction for a second. It's MVF minus what? MVI. All divided by what? T. Okay. We are super duper close to getting this all the way through. Did it get uglier or nicer to you guys? It's kind of ugly right now. Do you remember what started this conversation? We're trying to look at a connection between two different ideas.
It was how to find something without like having it. How to find A without having like A.
So, like, maybe it worked out, but we're really digging into this connection between force and momentum, right? I'm bringing that up for a very specific reason. This is kind of ugly, and I get it. However, what is MVF? Mass times velocity.
Mass times velocity. Final.
Sure, but what's mass times velocity?
That's not. Is rho?
It's momentum. This is momentum, so they're automatically connected here. As we look at this, what we have just worked out, and again, the significance doesn't feel like it until we start using it, but what we have just found is that if you take an object's final momentum and you subtract from it its initial momentum, MVF and MVI, and you divide it by time, we have a completely different way to work out force all of a sudden. Rather than knowing mass and acceleration, maybe we only need to know momentum and time. And we can start seeing that, hey, there's connections to be made, whether or not we use them right this second. Liam, how much money you got? Yeah, you can go. Okay. Now, this whole idea, the big takeaway, and we're going to see this happen over and over. There is more than one way. There is way more than one way to calculate force. Now, each of them are going to vary in which one you use, depends entirely on what you're given and what you can identify within your problem. Vince, I'm going to put your computer away for now. Okay, as we go through, we have a big idea, and I'm sure we've already talked about some of it, but I get this class mixed up with others as well. Momentum is a big idea, and it relates to other stuff. Can energy be created?
Like what? What do you mean?
Just in general, can energy be created?
No.
Ooh, I love that you heard both. Why yes? It is. I like it. But I think we're going to be able to tweak it a little bit. You said no. Why?
Because I remember talking to you about when you said, I'm thinking about perpetual motion. That's what I'm thinking about. Free energy.
Okay. Yep.
That doesn't exist. That's what I'm thinking.
So check it out. We're going to try to create some heat energy real quick. Put your hands together. If you're really cold, what are you going to do? Okay. Does it feel from your perspective like you're creating heat?
Yes.
Now, keep doing it for a second. And don't like hurt your hands. Anybody's arms starting to feel a little tired?
No.
Why would your arms start to feel tired? Oh my gosh, you're taking the energy from your arms to move your muscles, to move your hands to create the heat. So let's think about this. Without using the energy that's already in my arms, could I have gotten that heat?
No.
Which means I didn't really create any new energy. We're changing how energy presents itself. Okay, big statement, I'm sure you've heard it before. Energy cannot be created, nor can it be destroyed. You cannot. All the energy that's in the universe right now will always be the amount of energy that's in the universe. Mass cannot be created nor destroyed, and that one feels probably more unnatural to you guys. Can you try to think of an example where you think that you probably do see mass is destroyed? Say it. If you burn something. Now, to be able to do this, we need a big apparatus. But let's say I had a container, a large container, and I could weigh it. And there's wood and air and stuff in it, and then a fire started in it. but none of the gas was allowed to escape. What do you think would happen with the weight of it? Would the weight change? Why? So, it wouldn't. It wouldn't, with one small exception. When you burn something, you're changing all of that matter into a different form, right? You're taking wood, for example, and you're turning it into ashes. You're taking all the gases in the wood and you're releasing them, but there's another form of energy that shows up with fire. Light. Now, Einstein's big idea says that energy equals mc squared. E equals mc squared, that's his famous one. All it says is that, hey, the energy that got released can be transferred back to mass and vice versa. Nothing is created nor destroyed, whether it's energy or matter. And another big idea that shows up right here, we get a big one. This is the most important part of this entire section that we're in with momentum and force. We get the law of conservation of momentum. Yeah. I don't like it. I can see how it looks like Y though. The Greek version of the Y is much cooler. When... Who's sitting there? Liam? You're good. Yeah, you can go. This is a Greek Y. Upsilon. Yeah, it looks like a trident. Okay, the law of conservation momentum. Really super duper easy here to knock out. Law of conservation of energy says energy cannot be created nor destroyed. The law of conservation of mass says mass cannot be created nor can it be destroyed. What do you think this is going to say? Cannot still. We're not going to switch it. Definitely not. What cannot be created nor destroyed? Momentum. So you're right. Energy can't. Mass can't. Matter can't. Turns out momentum can't either. So really easy to knock out. Momentum cannot be created nor destroyed. Now I'm going to leave a little ... here because I don't want this to mislead. The idea of fire is a good thought to try to get rid of energy or matter and all those things. It can't be destroyed, only changed. Now, anybody happen to have a fidget spinner in your bag? Man, oh yes! Can I borrow?
What?
Wait, actually? He's been waiting since 2018.
He's been waiting since 2018 for this moment.
Ooh, how about a kendama while we're at it?
What? A kadama?
A kendama.
What's that?
Oh,
They're
it's
the
like
ball.
Oh yeah.
It's the string with the ball and the holes.
And
And
then you gotta catch.
all right, I will find a fidget spinner at home this weekend. Okay, how many of you guys played with fidget spinners, whether you have one today or not? All right, so let's say you had a fidget spinner and you go, and you spin it and you turn your hand. Do you feel anything weird about it?
Yeah.
What do you feel?
I
It's harder to turn one way than it is the other, right? Why?
But like air rolls on.
It would do it in a vacuum too, though.
It would?
The carnival ride.
So similar. When it's going, it has some mass. It's spinning at some speed, which means it has a bunch of what? Mass and velocity.
Momentum.
Holy cow, it has a bunch of momentum. And it wants to keep spinning. When you try to make it turn and you change its direction, it has to take some of its momentum and transfer it somewhere else. Turns out it transfers into your arm, and that's what's making it feel weird when you twist it. All that spinning stuff gets used all over the place. The reason that we use it, if you want to know what's level in space, but you don't have a way to drop down, that could be a challenge, right? Turns out, though, if you have something that just wants to stay balanced because of its momentum, like, I don't know, something fancy like, I might have a few of them. Something fancy like these guys. You ever seen one of these? It's kind of like a top. You guys ever seen one of these?
Oh yeah,
Oh,
I think
yeah.
I
It's a gyroscope.
No, you put it on the rope.
Is it like a tire?
It is. I'm gonna have to play around with these.
With it kind
Oh, I wish I had just a can of air or something.
Yeah,
Well,
like-
that broke it. I didn't do that. All right. So as we're going, I'm gonna bring a fidget spinner on Monday so we can feel that. You're never changing or you're never destroying momentum. You can change it. Now, anybody ever heard of a Newton's cradle? Can you tell me what it is?
I've heard of it.
Okay.
Oh, wait, isn't it that thing with the metal balls?
It is.
Yeah.
Yes.
Okay. You guys ever go to the PCR and play pool?
No.
Okay, so if you don't typically do it, that's okay. Everybody know what a pool is? Okay, so imagine that you are good at shooting the ball straight, and you slam the cue ball straight at another ball, and it hits perfectly head on. Is it possible the cue ball comes to a complete stop?
What? Yeah.
Complete stop.
Yeah, like if I have a cue ball here,
Doesn't have to transfer all of
and it goes here, is it possible that it hits this second ball? So ball, I'm just going to say 1 and 2, even though it's not the cue ball, it doesn't have a number. Is it possible that 1 strikes 2 and then 1 is completely still?
Yes.
Yes.
Okay, you have to do it perfectly, right?
Is it really a complete
Oh, it can be. Absolutely, it can be. Now, as you're looking at this, let's just think about what really happens here, and you're going to be able to make sense of this. Let's assume that we have a nice new pool table. We have this ball. I'm going to call it ball A. And it launches, let's say, how fast are we going to shoot the ball?
100?
Holy cow, okay. 100 meters per second.
Isn't it like 40-some miles an hour?
Yeah, that's really fast. 220 miles per hour. They are slamming it. Okay, and then we have ball B. This is its velocity of ball A. And ball B, here it is, just unsuspectedly, waiting at the velocity of 0.
You got E-train.
We can't talk about that show in here. All right. Love it, though, just for the record. Cool. All right. What's going to happen if this ball rolls forward?
It will hit the.
It's going to hit it. Now, if we pretend it goes perfectly, I'm just going to use this yellow arrow to say, hey, check it out. Time clicked, because I don't have the SpongeBob transition. All right. Is it possible that this is what happens afterward? Here's ball A, and it lives at velocity of ball A is now 0 meters per second. Could it happen? Now, realistically, at these speeds, you're going to just destroy these balls. They're going to crack, like it's going to happen. But if I now ask then, okay, well, tell me what you think about ball B. I bet you all have the same intuitive feelings and thoughts about this. What's going on with that ball?
It's gonna go fast.
It's going to go fast. How fast would you say it's going to go?
Probably like 50. Probably like 150.
It's not going to lose any energy on the way.
If we are able to hit it, if it hit all of it straight on so that it came to a complete stop, all of its energy was moved to where? So if all the energy was moved to ball B should be moving how fast? 100. Now, in reality, does it work exactly perfect? No, in reality, if you could hit it, even if you could hit the ball completely perfectly, I bet you'd see like 99.8 or something like that meters per second. Where did that extra energy go if we can't destroy it?
It had to hit the ball. Or like. It had to like. I don't know.
Into the pool table.
So probably some friction, for sure. It's rolling friction, which is more complex. I want you to do something for me. I want you to use your muscles to control these things and clap, but I don't want you to use any energy.
What do you mean?
Right? You can't do it. Now, if you use a little bit of energy, what happens?
Make a sound.
Oh my gosh, what do you think that sound is carried by?
Hands.
Sound waves. And how do you make sound waves? By pushing what into the air?
Air.
Energy. We're losing a little bit of our energy here. Would you hear a click?
Yeah.
There's some of your energy. Friction, the click of the ball. How many fingers can you snap?
I don't know how to snap with this one.
Can everybody snap with the middle finger?
Yeah.
Can you snap with the index?
No. What?
And then you can go. And you can get it going really fast if you get the timing right. You just throw in that, and oh, you just get all crazy. Okay.
No.
What happened?
Weird. I don't know.
I didn't hear nothing.
It's oh, I knocked mine.
The gas light is crazy.
What a weird noise this just made. All right. So we're nearly done with this. Is momentum destroyed here?
No.
No, it was only what?
Trash.
Transferred. Changed is okay. Yes, sir. Yes. Okay. Last little tiny piece. I don't even know how much we're gonna go into this. If you were standing, anybody in here ever roller skated
Yes.
or ice skated?
It was so sad though.
Ice skating.
Ice skating.
Stood on a skateboard?
Oh yeah. Yeah.
Okay. So pick whichever frictionless idea that you want to think of. If I'm standing on roller skates right here, and I take this thing and I throw it that way, this will go that way. What happens with me?
You might go
You
back.
stay there.
You sit it?
I might stay still or stay here if I can like try to absorb the impact. But let's do it bigger. Let's say I have a bazooka.
Maybe you'll.
And I'm gonna launch a bazooka that way instead.
You're gonna get pushed back.
It's gonna push me back, right? Now, that idea, like, it really does happen. I think I commented to this class the other day that movies lie about it, because they definitely lie about it. If you get struck by a bullet, you don't shoot 10 feet away, because bullets don't have that enough momentum, because you weigh a lot more than it. Now, paintball gun, same thing, like, doesn't happen. How does a rocket work? That's a big question.
Gunpowder.
Okay, so let's see. How does a plane fly? What's it do?
Fire. No.
No, a plane. Let's focus on a plane.
Fan.
Okay, so a plane is basically a fan, right? So here's a plane, and it has its propeller doing this sort of thing, and it does what? So it spins. So why does that make it fly?
Or doesn't it push the air
Push the
with
air.
its wings?
Yeah, I'd say either one of them. It pulls air in, and it pushes it back, right? Like, that's how planes work. And eventually you get enough speed going on this, and you get the right angles and stuff, and you can start flying. Okay, can planes fly 30,000 feet high?
Yes.
They can. Can normal planes fly 40,000 feet high?
Maybe not. Maybe.
Getting harder. 777 could. Fighter jets could. What do you think the Saabs that we fly out here, could we fly at 60,000 feet?
Probably not.
Why?
Air
The
tightness.
air is really light.
Okay, so the air gets less dense. And same idea, but I like it. Okay, what about at 100,000 feet? Definitely not ours. Could fighter jets still fly?
Yeah.
Yes.
What about at 200,000 feet? They're starting to struggle there because jet engines work by sucking in air and shooting out air. All right. Does space exist? Do humans go to space? Do humans have to control motion in space?
No. Yeah.
Yeah, right. You have to. Like, imagine an astronaut that's out floating around. He has to get back to the ship. He just uses little jet boosters, right? Like that sort of thing. Okay. Oh, for sure. For sure. Now, here's a weird idea. Planes and jets, they fly because they suck in air and push out air. Right?
Yeah.
Is there air out in space, though?
No.
So what the heck makes those move? How on earth do you control if there's no air for you to push against?
Press there.
So, why would that have anything to do with it? That sounded really aggressive. It wasn't supposed to. I'm just trying to counter you. There's no air in space.
Why is that?
Because it's a vacuum. Sorry? All the air is stuck to our planet via gravity is the real answer to that. Now, have you guys ever fired a hose, like a water hose?
Yeah.
When you squeeze the trigger on a hose, it shoots water out the front, right? And that same force that the water's, or that it's pushing on the water to make it go, pushes what direction? Back at you. There's no air needed for that. You could do that in a vacuum and you would still feel it. You're feeling the thrust created just by that nozzle inside, causing the pressure to push against and against. This is Newton's third law, saying, hey, if I push something out that way, it pushes back the same strength. That is all that it takes to make a rocket work in space. We don't need air. We just need that idea of conservation of what? Conservation of something. It's just conservation of momentum or energy, whatever you want to call it. Okay, that's the end of our chapter, guys. So right now, so you don't have homework over the weekend, I want you to work through the assignment, and we're going to do something a little bit different this time. We are going to do a practice test. Rather than just a review day, we're going to do like a full practice test so that we can work through these and hopefully clear up any misconceptions prior to the test. It'll probably be a team test, yeah. So we'll do a team quiz is what I'll call it. It'll be a practicing that you do with your neighbors, where we'll talk about that on Monday when we look at it. But beyond that, I do want you to make sure that you can demonstrate your understanding here. And it's like we have just enough time for a note quiz if we wanted it. Just throwing that out there. Yes. I don't think that's the way it's pronounced. All right. So, right, meow. Hopefully within the next 11 minutes, you guys can knock this out so you don't have any additional homework. You get the privilege of working through on October 3rd. That's today. That's not that day. Boom, 1, 2, 3, 4, 5. You get homework 3.3, which you will find waiting on page 80. I want you guys to knock out 22 through 28. So let's see, 3. I mean, if you don't finish it in the next 11 minutes, finish it at home, but get a good start on it. A lot. It depends on the mood.
I wonder if people are actually
Game of Thrones.
I watched it, yeah.
Wait, so you've seen all?
Oh yeah,
Some of them are dumb.
You watch Gen V too?
I did.
Until 5.
5 a.m.
Yeah.
That's kind of oh.
Oh, never mind. I'll stay up till. Oh, better. I'll sleep until 3:30. I think it's gonna be long.
Saban, do you have access to your power school?
I only have access when I'm on my work computer.
It's Aaron.
Yeah,
son.
Do you use Google?
Wait, so is that like a team quiz?
yesterday the only thing I did
Do you use Google Chrome on your phone? If you log into the same Google Chrome that you use, your import or your stuff will be your password will be saved. Hey, welcome in. I got this. Okay. Did you check back into the office? Yeah. You did? Probably fine. That's okay.
Okay, ask me. Let's act.
I can. No, now they just let us.
Alright, gotcha, man. Hey, I will post a video before the end of fisheries. I will get you a little wire stuff.
That's a quarter.
He was talking to me.
I know what did you do?
What pencils? Any questions?
Okay. It was only last year. Okay. Yeah.
Oh, you got last year.
Yeah.
Okay, JD. Not that, but we'll tell you your business. That's what I did. Will.
Open the parachute and reach terminal velocity.
It's so that you stop when the party's going.
But you should drop because you're
I have a few downloads right now.
That thing where you have to like rip them on the stomach and then you flip over.
That one was so hard. The one where you flip over to the back.
I can only flip over.
Yeah, the flipping back one was where you have to put more like that momentum.
I hope we don't do that again.
I'm doing barrel rolls is the funniest thing ever.
I know why.
This one.
Roll like sideways.
I'll have decisions.
No, that.
I'll help you.
I can't do that.
To be honest, I can't.
You're like roll your way. You want to have Sean.
When I got home, I started to I got home, I like throwing them out of the closet. I was like,
Yes, sir.
So probably next week we're gonna have everything turned in, all the list you gave me.
Good.
Let's do it all together.
Okay. That sounds good to me.
Is there homework today or?
There is.